It's June 24th, 2022. I'm Todd Dunn, and today I'm aboard my 1972 Allied Princess Ketch Sequester, which is a good place to be to talk about buying an old fiberglass boat. And in particular today, I want to talk about another major system on the boat, and that's the hull. I guess, you might say that is the boat. Why do we want to talk about the hull? Well, there are a lot of things that you need to be aware of when you're looking at an old fiberglass boat in terms of the condition of the hull. And in order to understand the condition of the hull, you have to know how the hull was built. Basically, there are several sort of categories of hull that you need to be aware of. The first is the hull solid fiberglass or is it cored? If it's cored, is it fully cored, the entire hull, or is it only cored above the waterline? Now, before we go on, let me just say what a cored hull is. A solid fiberglass hull is pretty obvious. It's just a hull made up of alternating layers, usually of chop strand mat and a heavier fiberglass textile. In an old boat like this one, say 50 years old, that fiberglass textile is usually something called woven roving, which is a very coarse but strong fiberglass cloth. And that method, alternating layers of chop strand mat and woven roving set in polyester resin, produces a very, very strong hull. Now, there are some limitations possible, which we'll talk about a little bit later. Anyway, so that's a solid fiberglass hull, just fiberglass fabric and resin. What's a cored hull? And why would a hull be cored? Well, a cored hull is a more complex hull construction. It consists of an outer hull skin, which is made up of solid fiberglass, but it's relatively thin. In most cored hull boats, it will be 1/8 of an inch thick or less. So in a boat made up of alternating layers of chop strand mat and woven roving, that means probably one layer of chop strand mat and one layer of woven roving. So it's a pretty thin layer of fiberglass. And then you have the core. Now, the core material, usually in an older boat, is something called end grain balsa wood. And that is basically balsa wood put in so that the grain, the orientation of the grain of the balsa wood, is perpendicular to the surface of the hull. And the idea of having it oriented that way is so that water can't propagate long distances along the grain if it gets into the core. And the core is bonded to the outer skin of the hull, usually with a paste made up of polyester resin and chopped up fiberglass fibers, and that's just coated on the inside of the hull, and the core is pressed into it. And then inside the core is another skin made up of usually the same layup as the outer skin. So it might have a layer of woven roving and a layer of chop strand mat in a typical cored structure. Now, why use core? Core is interesting in that basically it turns your fiberglass structure into sort of the fiberglass boat equivalent of an I-beam, and which makes the hull very stiff with a minimal amount of heavy fiberglass in it. So you can build a light hull that's just as stiff as a hull that might have been 3 or 4 times as heavy with additional fiberglass by using core material. And that saves on production time, Laying up a cored hull is quite a bit faster than laying up, say, 8 or 10 layers of fiberglass. It is a little expensive in that the core can cost as much or more than fiberglass plus resin. But by putting, say, an 1/8 inch skin, a 1/2 inch of core, and an 1/8 inch skin in, you'll produce a structure that is considerably stiffer, more resistant to bending and flexing than, say, 3/8 inch or maybe even a little more of solid fiberglass. So you get a very stiff, lightweight structure using core material. And those are the main reasons that core is used. Save on polyester resin and fiberglass, produce a lighter boat, and produce a very stiff boat. Now, that sounds wonderful. And those are all things you want to have. Why is core something you need to really be aware of and look into? Well, a core structure is only as strong as the bonds between the core material and the inner and outer skins. If those bonds fail through a process called delamination, then what you end up with is a structure that's not really much stronger than either the inner or outer skins. You go from a very stiff, rigid structure to a very flexible, easy to deform structure. And if you take a layer of fiberglass and make it easy to deform and flex it a lot over time, you'll develop stress cracks in it and you will have failures. So core structures, as I said, depend on the bonds between the core material and the fiberglass skins on the outside and on the inside of the core material. Now, what can cause a core skin bond to fail? Well, on an old fiberglass boat, probably the biggest source of delamination or core fiberglass bond failure is getting water into the core. And the water then, particularly if it's balsa core, rots the core and destroys your bonds. And there goes the stiffness and overall strength of your structure. So one of the things you really want to do if you're looking at an old fiberglass boat is find out if that particular make of boat had a cored hull, and if it did, where the core was. If it's just above the waterline, well, you got a lesser chance of getting water into the core than if it's below the waterline. The problem with core is that, as I said, if it gets wet, it can delaminate and the structural strength of the hull can decrease dramatically. And when that happens, that area needs to be repaired. And that usually means removing either the inner or outer skin, removing the failed core, and continuing to do that until you get to an area where the core is firmly bonded to the skins. So you can end up removing a lot of core material. Putting in a new layer of core, bonding it to the outer skin, assuming that's the one you left, and then putting in a new inner skin that's strongly bonded to the core material. Now, in a fiberglass boat like this one, working from the inside could be a real problem because there's furniture everywhere. It's built into the boat, and to get access to large areas of the hull to do a core replacement from the inside requires tearing out large parts of the interior. And that is time consuming, and if you're hiring it done, it's really expensive because building a new interior in a boat is actually a very significant, something like 80% of the time and cost of building a boat. So if you rip out a bunch of the interior structure and you're paying someone to do it, you can generate a very, very costly repair in short order. You can also do a core replacement from the outside. The negative of that is that you really have to worry about cosmetics. Once you have cut the outer skin off, remove the core in an area, replace the core with new material, make sure it's well bonded, put new skin on, well, then you have a rough surface, even if you use something like peel ply, that has to be faired to the rest of the hull. smoothed out, faired out till it's nice and smooth, and then you're either going to have to spray gel coat on and spend a lot of time sanding it, or you're going to have to paint the hull. And usually a core repair on a hull is going to require painting the entire hull, and if you're paying to have that done, it's very expensive. It can cost hundreds of dollars per foot of the length of the boat. So that is those are the reasons you don't want to have to do core replacement if you can avoid it. So you need to be aware if the hull of the boat you're looking at is cored, and you need to know how to assess whether or not the core is in good shape. And that's relatively simple. Usually what you do is just take something, a plastic mallet, for example, or I use a screwdriver handle, a plastic screwdriver handle, and tap it against the hull like that. If you get a nice sharp sound, that means that there's no delamination. But if you're tapping along and you get to a spot where the sound is very dead, not a sharp, clean sound, that probably means that you have some delamination, and you may also have wet core. You can also use a moisture meter, not so much for the absolute readings, but for changes in reading. So if you have an area that sounds good when you tap it, and you put the moisture meter there, you'll get a reading, who knows what it'll be, and you move into an area that sounded dead, chances are you'll get a much higher moisture reading. And that's usually an indication that you have wet core and delamination. So you need to get that fixed or walk away from the boat if it's significant in terms of the area, or you don't want to have to do that kind of repair. So that's cored material. Solid fiberglass hulls have their own issues, but they're not as big an issue as a cored hull. You can simply grind out an area and reglass it if it seems like there's some delamination or there's damage to the fiberglass. But it's relatively easy to fix and much cheaper. And you're also less likely to have a delamination problem in a solid fiberglass hull. But no matter what, it pays to go over the entire hull and sound it with a screwdriver handle or a plastic mallet, and look for areas that sound different than known good parts of the hull. In other words, you get a sharp sound. If you get an area with a dead sound when you wrap it, then you need to worry about it, and you can take some chalk or something and mark that area, and then go back and look at the boat after you finish and decide if the amount of repair that's going to be necessary is worthwhile. And if you want to do it, even, it may be worthwhile, but you don't want to do it. Now, another thing with fiberglass hulls, particularly in boats from the early 80s, is something called osmosis. And this happened because fiberglass resins in the latest 70s and early 80s had a formulation change, and it caused some issues with moisture absorption into the fiberglass resin part of the hull. And remember, fiberglass is a mixture of resin and fiberglass fabric. The resin saturates the fabric, and when it sets up, it makes it stiff and hard. And the fabric provides the strength. If the resin fails, then you have basically loose cloth, and your hull really isn't much stronger than that. So what happens with osmosis is water seeps into the hull and in various places and dissolves part of the resin and forms a pot of acidic liquid, which then dissolves more of the resin, and so on. It's a sort of positive feedback situation. And this will show up as what are called blisters on the hull. You'll look along the hull, see a nice smooth surface with a little bulge. That bulge may well be a blister. And what you want to do is look over the hull, and if you see any blisters on it, you might want to take a sharp implement, an awl or a very sharp pointed screwdriver, and pierce that spot. If liquid comes out, then you know you have an osmotic blister. Now, osmotic blisters are not a death sentence for a boat. They can be repaired, particularly if there aren't many of them, but some boats from the early 80s had hundreds of osmotic blisters, ranging in size from the tip of my thumb to like this. And if you had lots and lots of big ones, the entire structure of the hull could be compromised, and the repair would involve grinding away all of the compromised fiberglass and building it back up with new fiberglass. And if you do it yourself, you can do it. It's very time consuming, and you do have to dry the hull out as thoroughly as possible before you do the repair. And that means a protracted period out of the water, in most cases at least 6 to 9 months, and in a humid climate, perhaps more than that. So that can cost a lot of money to put the boat in a building for that long, to let it dry out before you repair it. So significant blistering is probably something to walk away from. You're going to find this mostly on latest 70s, say 79, to early 80s boats up to about 84. That's when it was most common. It can happen pretty much at any time. If you just have a few blisters, you can pierce them, drain them, grind out the bad fiberglass, repair them, fair them out, and then do a seal on the hull. And blisters are mostly going to be below the water line, where the hull is in the water all the time. So you have to remove the bottom paint, and once you've removed the bottom paint and repaired the blisters, you can barrier coat the hull with special epoxies, which are much more resistant to water ingress through the epoxy layer, and basically stop the possibility of future osmotic blistering. Because if you can't get moisture into the hull structure, you're not going to have osmotic blistering. Now, this is a big job. I did it on this boat. I was working on weekends at the time, and it took me about 8 weekends, working about 20 hours a weekend to finish the job. Because I think I had the hull sandblasted to get the bottom paint off. I then ground out all the imperfections, filled them all with thickened epoxy, sanded the entire hull fair, and then rolled on 6 coats of epoxy barrier coat, and then re-bottom painted the hull. It's very time consuming. The materials, if you did it now for a hull this size, 27 feet on the waterline, and full keel, so relatively large wetted surface area, probably cost $800 or $900, plus rollers, masking tape, etc., and lots and lots of sandpaper. So you could easily spend $1,500 to $2,000, or if you include removing the bottom paint, maybe as much as $3,000 to barrier coat a boat like this. If you do the labor, if you pay to have it done, it's going to cost a lot more. So that's something to look at. Blisters are something most people are going to walk away from, because if a hull has just had blister repair and has not had a barrier coat put on it, that means that the rest of the hull that wasn't repaired is still susceptible to blistering, because the same resin was used for the rest of the hull as was used in the spots where the blistering occurred. And you're probably going to have blisters popping up every year or two that you'll have to repair. And if you let them go, you'll haul the boat out sometime and find a lot of blisters that you have to repair. So it's something to consider when you're looking at a boat. Is it blistered? Have they been repaired? Is there good proof that the boat was barrier coated? Okay, the other thing I wanted to talk about is keel types. Now, I don't want to go into the merits of different keel types. I just want to point out the two primary types of keel you're going to find on an old fiberglass boat like this one. And they are a keel with internal ballast. This boat has internal ballast, where the hull of the boat includes the keel. The keel is fiberglass, and that it's hollow, and the ballast, in this case a lead casting, is set into that hollow with fiberglass resin to bed it in and then glassed over on top. A boat with internal ballast doesn't have keel bolts, and the keel can not fall off even if you hit a reef with it, because the keel is an integral part of the fiberglass hull. I'm not saying you can't damage it, but it's gonna, unless you really let it sit on a reef for a long time and basically grind the keel off, it's still gonna be there. And that is something you might want to consider. A full keel boat will almost always have internal ballast and will consequently not be susceptible to damages from grounding that are as significant as the case with a boat with external ballast. Now, if your boat has external ballast, you have other considerations. The other factor with internal ballast is, what is the ballast? The most common materials are lead and iron, and some boats actually have concrete ballast. Usually what's called heavy aggregate concrete, but concrete ballast. They just poured some concrete into the keel. Lead is obviously the best because it's the highest density. It's going to put the weight of the ballast down the lowest and provide the most stable platform. Iron is much less dense than lead, so an iron keel will have more of its weight up higher, and the boat will not be quite as stable. And a boat with, say, concrete ballast is going to have a very low density ballast, and you're either going to need a lot more ballast weight because you'll have a lot more weight up high, or you're just going to have to deal with a tender boat. So the type of ballast matters. Lead is best, iron is sort of second, and things like concrete are sort of a distant third. So you need to look into how the boat is ballasted. Now, even if you have lead, there's another consideration. Is it a single big casting of lead that was made to fit into the keel cavity and basically fill it up? That's the best case. Or is it a whole bunch of little ingots and pieces of lead that are just put down in there, and then polyester resin is poured over them to lock them in place? That's not as good as a lead casting because you have a lot of polyester resin filling the space between the pieces of lead, and the weight of the ballast is not as low, and for the same weight of ballast you won't get the same amount of riding moment or stability from the keel. Now, iron keels also come in solid form and also in basically chunks of iron that were put into the keel cavity and glassed around. So that's a consideration. And you may even find some iron keels where they poured concrete over them to seal them up. Now, another thing about iron keels is that iron rusts if it's exposed to water. Rust, iron oxide, has a higher volume per unit amount of iron than iron metal. So if your keel gets water into it somehow, you hit a reef and break a hole in your fiberglass part of your keel, and a little water gets in, it can't get into the boat because the ballast is sealed in there, but it gets into the ballast area. That ballast will rust, and the iron in there as it rusts will expand, and that can put a huge pressure on the fiberglass structure of the keel and actually crack it and damage it. So if you have a boat with an iron keel, you want to in terms of iron ballast inside an enclosed keel, you want to make sure that the boat hasn't been grounded, or have good evidence that if the boat was grounded and there was damage that allowed water into the keel cavity, that it was repaired immediately. If it sits in the water for another 4 or 5 months or a year after a grounding, even though the boat isn't going to sink, probably won't be significantly affected in terms of sailing ability, you can have structural damage to the fiberglass part of the keel, which is not good. Now, that won't happen with lead. It also won't happen with concrete ballast. That brings us to the other kind of ballast, external ballast. External ballast is on the outside of the hull, and it is always bolted on in some way, usually with keel bolts that are put into the lead when the lead is cast. So they're basically an integral part of the ballast keel, the lead keel or the iron keel. Now, external ballast keels are good in that they're always a single casting, so you don't have to worry about a bunch of little pieces. But they're bolted to the bottom of the boat, and they're only as good, as strong as the attachment between the ballast and the hull. So you need to look at how the external keel is attached to the hull. You need to find out where it's attached and look at the bolts that come up out of the keel through the bottom of the boat and how they're held in there, usually with large nuts, and sometimes just with very big washers, sometimes with pieces of flat bar, that the flat metal bar that the keel bolts pass through, that may or may not be glassed into the structure of the boat. But ideally, what you want to find, in addition to where the keel bolts come in, is that there is a structural fiberglass grid inside the boat that the keel bolts pass through, so that the load from the keel, which can be very large, many tons, is spread out over a large area of the hull. You do not want a keel where the bolts simply come through the bottom of the boat along the center line, and they're just big washers, maybe even say like that, on the 1-inch keel bolts and nuts holding them down. And that's it, because then you have all the load from the keel concentrated in a very small area of the hull. And if you ever hit anything, or even if you sail the boat in heavy winds and waves with pounding and a lot of heel, that can weaken the structure of the hull. And it's entirely possible with that kind of attachment that at some point the keel might fall off. That's never good. So if you have an external ballast keel, you want to make sure you understand how it's attached, that there is a good structural grid inside the hull that spreads the load from the keel out over a wide area of the hull, and that that grid is well bonded to the hull, and that the keel bolts pass through the grid as well as the hull and are secured properly, and that the nuts on the keel bolts are tight. And if the boat's out of the water, you also want to look at the joint between the top of the ballast material, lead or iron, and the fiberglass of the hull, to make sure that that surface is in good shape and that there's no sign that water might have been leaking in there. Because water that leaks in will get to the keel bolts. It will be an anoxic environment. If you have stainless steel keel bolts, that will lead to crevice corrosion, and the keel bolts can consequently fail. So it's important to inspect that, know what kind of attachment the external ballast keel has to the hull, and inspect it and make sure it's in good shape, because repairing it can cost a lot of time and a lot of money. Okay, so that sort of covers the things I wanted to look at with a hull. There are other things, but they're less important. Those are the big ones that you want to look at. Now, I was going to include information about the deck, But this video has gotten pretty long, so I think I'm going to end it here and say, if you enjoyed the video, please give me a thumbs up. And if you haven't, why don't you consider subscribing to my channel and clicking that notification bell so you'll find out when my next exciting video is posted. Thanks for watching.